Hi, this is Gary Millett. This is ELE 110, Electronics for Technicians 1. This is the fall of 2022. This is topic 13B, electrostatics, magnetism, magnetism, and transformers. I'll try to spit that out. Let's get going. So we'll start off with the magnetic field. And before studying the magnetic field, let's review electric fields. Electric fields is a topic of electrostatics. The basics are that like charges repel, unlike charges attract. And a well-defined force exists between charges. It is proportional to distance and proportional to the amount of charge. So the definition of electric field is we define an electric field to exist between charges. The direction of the electric field is the same as the force between the charges. So here's a little picture, a plus and a minus. The electric field goes from plus to minus, and therefore the electric field is in the direction of the minus charge. And a force of attraction will exist between the two charges. So if I have two metal plates connected to a battery shown here, with the plus side of the battery on top and the minus side on the bottom, note that an electric field is always perpendicular to a conductor and is pointing towards the minus side of the battery. Two charged spheres, plus and minus, and notice again the electric field comes off perpendicular to the spheres. Now, if we talk about magnetic fields or magnetostatics, magnetic fields may be produced by naturally occurring phenomena, magnets, or may be induced by the flow of current through a wire or a conductor. The little sketch here shows a wire with a current I going through it, and there's a magnetic field which wraps itself around in circular loops around the wire. The magnetic field forms loops around the wire as shown here. The strength of the field is proportional to the current, I. Magnetic fields, again, magnetostatics. A bar magnet is also a source of a magnetic field. So this little diagram shows a permanent magnet with a south and a north pole. The magnetic fields form loops. Like poles repel and unlike poles attract. Here we have two more pictures, and the top one shows the south and the north pole attracting one another, and the bottom one shows the north poles opposing one another. So the force on the top is to pull them together, the force on the bottom is to push them apart. Lines shown here to indicate the magnetic field are called flux lines. The more the lines of flux, the stronger the magnetic field. In this figure, we show a magnet, bar magnet with north and south poles, and then we have two materials like glass, for instance, and glass is not magnetic. It is non-magnetic, and therefore it doesn't affect the flux lines around the magnet. On the right-hand side, we see soft iron, and it turns out, notice the soft iron, which is ferromagnetic, or a magnetic material, can affect the path of a magnetic flux. It alters what the magnetic lines of flux do. Here's the Earth's magnetic field. We should know that the Earth is actually a large magnet. And it turns out we talk about the north magnetic pole and the south magnetic pole, and they're actually off of the geographic north and south pole. Fortunately, we have the magnetic field around the Earth because it shields us from the radiation of the sun. It is also the cause of what? The aurora borealis, the northern lights. What about magnetic flux density? Well, the amount of flux per unit area perpendicular to the magnetic field is called the flux density. Its symbol is B, and the unit is the Tesla, T. 1 Tesla equals 1 Weber per square meter, and the equation is shown here. Question might be, how do materials become magnetized? Well, small magnetic domains line up in a material when it becomes magnetized. And of course, since the Earth is a large magnet, any type of ferromagnetic material eventually, if it's just in the one place for a long time, will become magnetized by the Earth's magnetic fields. So in this figure 10.4, these little blue-shaped objects, which are all random on the left-hand side, aren't lined up, so therefore there's no magnetic field there. On the right-hand side, notice they've been lined up due to the force of a strong magnetic field, and there's a north and south pole now to that magnetic material. So what about some permanent magnet applications? Well, here we see magnetic switches. The one on the left shows the switch is closed when it's close to the magnet. And there's two leads that go into that top box, so they're connected, or there's a complete circuit there. If the top box is taken away from the bottom magnet, as shown on the right-hand side, what happens, that switch would open up through the spring, and we would have an open circuit which we could sense. This is very often for safety. We do this on windows and doors and so forth for alarm systems. And that's shown right here. There's a transmitter unit. Notice window 1, 2, and 3, and the magnet and the box with the relay in it. And this is a typical perimeter alarm system. Now, that brings us to electromagnetism. As mentioned previously, the flow of current in a conductor produces an electromagnetic field around the wire. That idea is shown here again in figure 10.8. Current going through the wire, we have lines of force around the wire. Actually, it turns out there's a right-hand rule that determines the direction of the field. So we show a typical experiment that you might do in high school with a battery in diagram A here of figure 10.9. You take and you have a wire that goes through a piece of paper, and it turns out you could sprinkle iron filings and they will line up with the lines of flux. There's also a compass in B that shows how the compass gets affected by the lines of flux. And then we notice that the lines of flux in lower diagram A and B, the current's going to the right in A, and the lines of flux are clockwise. The current is going to the left in B, and the lines of flux are counterclockwise. And here's an illustration of the right-hand rule. The current, in this case, is conventional current, not electron flow. The conventional current shows charge going from the positive to negative, which you know is not true today. And you hold your thumb in the direction of the current, and the flux lines are given by the direction of your fingers, are curling. So there are some electromagnetic properties of materials. There's something called permeability, mu. That's the ease with which a magnetic field can be established in a material. And there's relative permeability, which is the mu of the material divided by the permeability of free space, which is mu sub naught. There's something called reluctance, the opposition to the establishment of a magnetic field in a material. Reluctance is given by L over mu times A, the area. Magnetomotive force, or MMF, the force that produces the magnetic field. F sub m is equal to N times I, where N is the number of turns and I is the current, as shown by figure 10.11 to the right of that equation. For the magnetic circuit shown here, the flux is given by F sub m divided by the reluctance of the core of that iron core up above in figure 10.11. And here's a picture of some electromagnets. Notice that depending on which way the current goes to the coil, we get a south pole on the left, a north pole on the right for figure A. If I reverse the flow of the current, I get a north pole on the left and a south pole on the right for figure B. What are some applications of electromagnets? Well, here's a read-write function on a magnetic surface. This is the basis for the operation of magnetic recording. You see the right head on the left-hand side, and a moving magnetic surface is under it. You put an input current pulse. This would be digital data being written on a magnetic tape with a right head and an air gap. The air gap is there to cause the fringing the magnetic field into the moving magnetic surface, which is on the surface of the tape. On the right-hand side, when we read the tape, the read head just puts out a little output voltage pulse, which has to be magnified or amplified as we pass the tape below the read head. Another operation here is a CD-ROM. You can't find many of those anymore, but it turned out this was a combination of using magnetics and electromagnetics and magnetic particles in a recording surface and a high-powered laser beam. So in A, you see an unrecorded disk, and the magnetic particles are all lined up in the same direction. Writing on the disk is in B, A high-power laser beam heats the spot, and the magnetic particles align with the external electromagnetic field that's from the electromagnetic above it, above the CD-ROM surface. Reading from the disk, a low-power laser beam reflects off of the reversed polarity particle, and its polarization shifts. If the particle is not reversed, the polarization of the reflected beam is unchanged. So again, a low-power laser beam there. If I want to erase the disk, external magnetic field is reversed, and the high-power laser beam causes the magnetic particle to align with the external beam, restoring the original polarity. So again, these last two slides are the basis of CD-ROM operation. And again, CD-ROMs have been replaced by DVDs, and they are a slightly different type of operation. So this brings us to a solenoid or relay. The basic solenoid is shown here, or in A, B, or C. So A just is a graphical picture of it. B shows the common or basic construction. There's a coil and there's a plunger. And the cutaway view shows that there's a spring inside the plunger. So an unenergized or no voltage or current, what happens, the plunger is extended. In figure 1017b, if the coil is energized, the plunger is retracted. So the theory behind the basic solenoid is fairly easy to grasp. When power is applied, the magnetic field provides the force to move a plunger, typically against the force of a spring. The magnetic field energy has been converted to motion. And here's a relay, a switch that's operated by a magnetic field. We talked about these in the prior presentation, but here's a different type of picture one, and this shows a coil with leads 4 and 5 connected to the coil. There's a normally closed contact, normally open contact, leads 2 and 3, and then 1 is the spring that is the contact to the armature. So 1 is the common lead, and right now it's in normally closed contact. 1 is connected to 2. When I energize the coil, what happens is the armature gets moved down, it's magnetic, and now what happens is the connection between 1 and 2 is opened, and now we have a connection between 2 and 3. And the symbol's on the right-hand side there. How about a loudspeaker? A loudspeaker is another application of a permanent magnet. So in part A of this figure, we see a permanent magnet with a north pole and a south pole, with the south pole is the center of the permanent magnet, and the north poles are the two extremes on top and bottom of that magnet. There's an electromagnetic coil, and it's connected to a flexible cone, and it turns out that would be basic speaker construction. Now, if a coil current produces movement of the speaker cone to the right, what happens is if I've energized the coil with a DC voltage there, and that will move the there'll be opposition and the coil will move to the right. If I change the flow of current DC-wise into that coil, it'll move to the left. So if I take and apply a sine wave where I'm alternating the polarity of the current through that coil, the electromagnetic coil in the center, it turns out it will vibrate back and forth, and you'll hear sound coming from the flexible cone. If it's in the audible range, that is above, say, 20 hertz, and below, say, 15,000 hertz, or vibrations per second. So the loudspeaker, we have the conversion of electric current into a magnetic field, and then motion and sound energy produced. And this shows the final aspect of this. Here I have an audio signal voltage going in through an amplifier to that magnetic core, and it turns out I get a vibrating cone and sound waves, and the sound travels to the right. Another electromagnetic device, a real ancient one, is the first analog current and voltage meters. Use electromagnetism for their operation. So this shows that there's a rotating coil assembly, coil wires, and a wire coil around the rotating coil assembly. And it turns out that there's a pointer, and as I pass current through that coil wires, or the coil wires on the rotating coil assembly, what happens, it forms a magnetic field which repels the north and south poles of the permanent magnet and causes the pointer to move. on the meter scale. The more current I pass through there, the more the motion. And that's called the basic directional meter movement. Here's another picture of this and shows the torque with the current in and current out shown on the right-hand side. Current in is a dot, current out is a like arrowhead or a cross. And it turns out that this figure 1023 shows when the electromagnetic field interacts with a permanent magnet field, forces are exerted on the rotating coil assembly, causing it to move clockwise and thus deflecting the pointer. So these devices could be made in such a way as to have a full-scale deflection when only 50 microamps of current was applied. Now 50 microamps is 50 times 10 to the minus 6 amps. But again, you could get that type of sensitivity. This slide is entitled Magnetic Hysteresis. We should know that the magnetizing force H is given as shown here, where this is a core. Now there's a number of turns N that is wrapped around that core. There's a reluctance of the core material. There's a length around the core of L. And there's a cross-sectional area A. And there's so much flux through the cross-sectional area. So the parameters that determine the magnetizing force H and the flux density B are the current and the number of turns and the reluctance of that core material. Now, the hysteresis curve is shown here. If I take and cause the current to go through a 360-degree cycle, I'll discover that I'll get this final curve in part G of this figure. And basically, the relationship between the B and H values is known as the hysteresis curve. In essence, the magnetization of a material is nonlinear and lossy. The fatter that hysteresis curve is in G, the more lossy the core is. Electromagnetic induction is the title of this slide, and it shows the basic principle that was discovered over 100 years ago, that I have a north and south pole of a magnet, and there's a magnetic field between the north and south pole. I take a wire and I pass it down through that magnetic flux, and it turns out it induces a voltage. If I take and move the magnetic field upward and the wire stays stable, I induce a voltage. The polarity of the induced voltage depends on the direction of motion. Here you see on the left-hand side, downward motion gives a plus to minus as indicated. Upward motion gives a minus to plus as indicated. Just the opposite. 180 degrees out of phase, if you will. So this slide shows figure 10.28 rather, the induced current on a load as the wire moves through the magnetic field. So if I have just this wire moving through a magnetic field, it turns out a current would be induced and would be passed through the load. This is called the generator effect. In this one, we call it the motor effect. I pass a current through a wire that's in a magnetic field, and notice there's an upward force on figure A here. If I take and notice now that in A, the dot was going, showing the current going into that wire, into the slide. On B, I have a cross, which means the current's coming out of the slide or towards you, the observer. And notice what happens. There's a downward force. So this is a principle. This principle is the basis for the operation of electric motor. We pass a current through a wire, and we have permanent magnets, and we can cause the wire to move. And of course, the wire is wound on a armature that can rotate. So this is more of a demonstration of Faraday's first observation. The amount of induced voltage is directly proportional to the rate of change of the magnetic field with respect to the coil. So this shows that I've got a south and north pole on a permanent magnet there, and I'm pushing it in. As the magnet moves slowly to the right, magnetic field is changing with respect to the coil, and voltage is induced. On the right-hand side in B, as the magnet moves more rapidly to the right, magnetic field is changing more rapidly with respect to the coil, and a greater voltage is induced. Here, we're going to take and This is a demonstration of Faraday's second observation. A magnet in A moves through a coil and induces a voltage. On B, a magnet moves at the same rate through a coil with more turns and induces a greater voltage. So that can be indicated by that equation there, that the induced voltage V is equal to the number of turns times d phi over dt is the rate of change of magnetic flux. So more applications of electromagnetic induction. Modern automobiles use a similar system for ignition and timing. This shows a crankshaft position sensor produces a voltage when a tab passes through the air gap of a magnet. So it turns out there's a magnet there, and if I take and change the air gap, it'll change the reluctance and hence induce a voltage. So the coil output goes to signal processing and a control circuit. And you see the steel disc and the protruding tabs. Here's some more applications. On A, it shows there's no changing magnetic field, so there's no induced voltage. Insertion of the steel tab, this goes back to the prior slide, reduces the reluctance of the air gap, causing the magnetic flux to increase and thus inducing a voltage. So that was the explanation which I already gave on the prior slide. How about a DC generator? This figure 1034 shows a simplified DC generator. I have a wire loop, I have a mechanical drive which turns that wire loop in the magnetic field of that permanent magnet, and there are brushes, and the brushes will take and allow the current to go to an external circuit. This graphic shows the relationship between the magnetic field and the rotating wire. Recall there are 360 degrees in one complete revolution. So here's a 4 steps which will take and show you a complete rotation of this DC generator with the wire brushes. Down in figure D, you see 2 humps, 2 halves of a sine wave, and that's the DC generator as opposed to using slip rings, which give you an AC generator. So the induced voltage over 3 rotations at a loop, first, second, and third rotation give you 6 humps. The voltage humps are half sine waves. And the induced voltage for a 2-loop generator is much less variation in the DC voltage that's produced. So on the prior slide you had distinctive humps. Here you have an induced voltage across an external circuit which doesn't change it too much in its amplitude. The AC generator just uses slip rings, and then you get an AC that the second hump is flipped over due to the slip rings, and you get an AC or sine wave out of the generator. So the big application of electromagnetic induction is transformers, and here shows a basic transformer. I have a transformer core, and it turns out the magnetic flux will flow in that transformer core. I have a primary winding of N sub P turns, P being the primary. I have a primary current of I sub P and a primary voltage of V sub P. And what happens is I induce a voltage in the secondary winding. It has N sub S turns, or secondary turns. I have an I sub S current and V sub S secondary voltage. And with this setup, I can change the voltage of the secondary from what the primary voltage is. So voltage is proportional to the turns ratio. This shows voltage of the primary compared to voltage of the secondary is equal to the number of primary turns divided by number of secondary turns. Also, you might notice that what happens is I can't produce energy. I can't get something for nothing. So if the voltage on the secondary goes up, the current on the secondary goes down. The power into the primary must equal to the power out of the secondary. So V sub P times I sub P will be equal to I sub S times V sub S. So modern design of transformers, you get toroids, and here's a picture of a toroid transformer. It's more efficient. Here's another picture of a toroid transformer. And there are 2 types, well, there's actually 3 types of transformers. I think I'll only show 2 here. Step-down transformer. So this one shows a primary of 50 turns, and there's 1,000 volts at 2 amps, or 2,000 watts, or 2 kilowatts being applied to the primary. Now, the secondary you can see is red, compared to the green primary windings, and there's only 10 turns. So it's 1/5 the turn. So what will happen is the secondary voltage will be 1/5 of what it is in the primary, or 200 volts, but the secondary current will be 5 times higher, or 10 amps. And you notice that 2,000 watts on the primary equal 2,000 watts on the secondary. Now, transformers are not perfect. They're pretty good. They're close to 98% efficient. So in reality, if there is some lost power, it becomes heat. It actually would heat up the transformer. Here's a step-up transformer. Now we have 100 volts on the primary and 10 amps. So 1,000 watts on the primary. There's 5 turns of green wire on the primary, and there's 20 turns of red wire in the secondary. Well, that's a 4-to-1 turns ratio. So what happens, the secondary now has 400 volts, but only 2.5 amps. You multiply that out, comes out to 1,000 watts. Again, you cannot get exactly 100% efficiency. Here's something you might be familiar with. On a pole, electric pole, we have high power transformers. The transformer is actually in a bath of oil to kind of cool off this transformer. It's a typical step-down transformer used in residential areas, used to deliver the 120 volt AC and 240 volt AC power to individual homes and apartments. It taps off of the 13,000 or 13 kV lines that are strung in the tops of the power poles. And again, if you could touch one of these in their operation, it would feel warm to your touch. Here are what you might find high-powered transformers in substations, and you don't find many of these because they're just such huge devices, and they can handle, if not 500 kilowatts, maybe a megawatt of power. Faraday's historical note of Faraday, you can look at this if you so desire. He was very much remembered for his contributions to the understanding of electromagnetism. So that's it for this guy.